and units. So we talked about how units are like important and stuff, and that you give an answer in meters that's supposed to be in meters per second. That can't possibly be right. So also we talked about how if you give an answer without any units, that's even worse. Because you don't even know what you're talking about and you're crashing over my spaceship. If we also talked about significant figures, which is how many numbers you give. Just because when you type 2 divided by 3 into your calculator, it gives you like 12 different sixes. That doesn't mean that's the right answer. You want to make sure that you understand the two rules that we have, which were that when you multiply or divide two numbers, the final number of significant figures corresponds to the least precise input in terms of the number of significant figures, like 3 or 4 or 2 or whatever. And when adding or subtracting, the result corresponds to the least precise of the input figures with respect to the decimal point. So either in the 10th place or the 100th place, whichever is the least precise input, is the one that corresponds to the final answer. We'll do some practice, more practice with significant figures in the practice problems that we're going to do today. So a reminder from your syllabus about where we are, right? We just started. We're going to spend this whole week talking about one-dimensional motion, which is fairly closely related to calculus. Those of you that have seen your calculus so far, we're going to sort of recap that in a physics kind of context, but mostly this is just about one-dimensional motion and how it might affect moving objects, and that's what we're doing all this week. Okay. So we're going to start by doing some pretty boring and basic definitions, because like we got to have some place to start here. So we're going to define what we call the word position. What we're going to say position is location with respect to another object or a coordinate system. Why is it just location? Why do we have to invoke some other thing? The answer is, oh, sorry. Yeah, answer. Could be anywhere. Could be anywhere. Okay. But what's the 0 point? Okay. Yeah, the question is, okay, where are you? I'm at 12. Okay, great. But it turns out there is no absolute 0 location in the universe. There's no center of the universe. When the Big Bang occurred, it occurred such that all of space is expanding relative to all of the rest of space. And there's no 0 point in the universe for speed or velocity or for position. So every single position that you ever measure has to be relative to something else. There can't be any absolute position in the universe. So before you've done any of the work, you need to define what your coordinate system is or what you're measuring relative to. So today we're just going to do a simple one-dimensional coordinate system here. We'll call it x, and we'll measure our position in meters there. All right, so I'll say we're going to measure the position of an object over time. We're going to get different numbers then for the position relative to that 0 point. So at one point I'm going to be here, and then a couple seconds later I'm going to be over here, and a couple seconds later I'm going to be over here. So we're going to make some multiple position measurements and plot them out on a graph. Many of you have not been taught how to make graphs. I know because I asked you to do them in exams or your predecessors, and you failed miserably. Okay, so here's how you make a graph. First of all, you need to label your axes. So this axis is going to be time. And you need to have units on your axis. So this is going to be in seconds. Okay? So we're going to define this x-axis to be time in seconds. We're going to label some of the numbers. Great. What are we plotting as a function of time? We're going to plot position. So you have to label the y-axis too. And we're going to plot it in meters. Of course, you can plot it in centimeters if you want. You can plot it in different types of units, but you need to make sure you label both the axes and the units of those axes. Okay? So let's go ahead and put in some numbers for our positions. Note that Excel does not know how to make a graph, okay? It's just embarrassing. If you're like a business major and you want to like snow your superiors, that's when you use a graph in Excel, okay? Like, doesn't understand the concept of the x-axis. It just thinks that each row that you have is a different value on the x-axis, and it comes out as a complete disaster. So don't assume that Bill Gates knows what he's doing, because he doesn't in this particular case, okay? So when plotting, of course, you're going to need to figure out where you are at any given time. So let's measure my position relative to this metal mark, which I'm not even sure what these are. They're covering up places where wires come out or something in the stage. Okay, so we'll call this point 0. So I'm going to start at point 0 at time 0. All right, so 0, 0, I'm going to plot my position right there. And let's say that over the next couple seconds I'm going to walk to the right, which is defined in the positive direction here. So over the course of 1, 2, 3 seconds, I've come over here. How many meters am I from my original position, do you think?
2.
I'm 2 meters high, so I think it's more like 5, something like that. Okay, I'm a little less than 2 meters, but, you know, pretty close. Okay, so let's say over the 3 seconds, at time 3, my position was 5. That's way up here. Okay? So, okay. Here I am. Okay, great. Now I'm going to run back the other direction in 2 seconds over here. So what position is this? Still have an idea? -6. Sure. So that took an extra 2 seconds. So now I'm at time 5 in a position -6. So it's going to be like down here. So let's assume that I was going a straight line in between those two locations. And then I'll walk slowly back over the course of another 3 seconds to 0. Okay? Come back. The final position there is going to be 8, 0. Okay. Alright, so let's go ahead and label these points, because we're going to use them. So this one's going to be 0 in time, and I'm going to give it 0.0. That's within a tenth of a second, say. Or a tenth of a meter. So this is in meters, comma, 0.0 seconds, 0.0 meters, let's say. And this is then 3.0 seconds. We're just going to call that 5 meters. I'm not sure if it's so accurate for it to be within 10 centimeters. And we'll call this 5.0 seconds, comma, -6 meters, and then 8.0 seconds, comma, 0 meters. Okay? So those are my positions as a function of time. How are we going to use that? Well, we have to find something else. Here's a new concept, a new definition of a word called displacement. And we're going to define displacement as the difference in two positions. Okay, so we're going to define the x position at time 1 as x1. And x2 will be the position at time 2. going to then define the displacement as delta x. We're going to define to be x2 minus x1. Okay, not that complicated. Who's seen this delta notation before? Who has not? Okay, no one will admit to not having seen it, okay. It means change in a quantity. We're going to kind of use that quite a bit over the course of the semester. So when we want to say we have two positions, what is the change in position? We just use the delta notation. The change in position, or in this case, the displacement, we're just going to show as delta x. Recall that an equal sign means the two things are the same. 3 bars like this means is defined to be. So this isn't like, oh, hey, delta x happens to be this. No, I'm defining it. Here's what delta x means at this particular point in the course. And so I'm saying delta x will be this. This is what delta x is going to mean at all times in the future. All right, well, that's like pretty basic and boring stuff so far. All right, how can we make this more interesting? Well, at least we'll make it modestly more interesting by looking at how those positions are changing as a function of time. So, of course, as position changes over time, that involves what we're going to define to be a velocity, or something that's, yeah, question. Question is displacement going to be positive all the time? No. Displacement has a direction. So in this case, let's take a look at, say we'll define x1 to be the first point and x2 to be the second point. In that case, right, the displacement is going to be 5 meters minus 0 meters, so that's to be positive 5. But if we take the displacement between the second 2 points here, now x2 is going to be negative 6 meters, and x1 is going to be plus 5 meters. So we have negative 6 minus 5. The total displacement here is negative 11 meters. So displacement can be either positive or negative, depending on whether x2 is to the positive side or the negative side of x1. Yep, good question. Okay. So velocity is a catch-all for changes in position, but there's going to be different kinds of velocity. There's like 3 different kinds of velocity. So already, I'm going to make things complicated. I'm going to start off with defining average velocity. So that one's pretty simple. Okay, your average velocity is just displacement divided by the time required to execute that displacement. So in this case, that average velocity is going to be equal to, yeah, question? I haven't really defined net displacement. So, I mean, displacement is just going to be the position at any 2 different locations. So the average velocity is not the total. So let's imagine the way we've defined displacement, right? What's the total displacement between time 0 and time 8 seconds? Well, at time 0, we're at position 0. And at time 8, we're also at position 0. So displacement is 0 in this case. And so the velocity is also going to be 0. The average velocity, all that time I was walking around the stage, the average velocity is 0 because I'm not talking about the net displacement in this case. It's just the total difference in position. So that's a good question because things are going to get more complicated, as I already alluded to. So we're just going to define average velocity as, don't try to do anything complicated. Just look at the positions at each of the times. Take the change in position, the displacement, divided by the change in time. And therefore you're going to get, x2 minus x1 over t2 minus t1. what is your average velocity? Well, in the previous case here, between 0 and 8 seconds, we have T2 is going to be 8 seconds. X2 is going to be 0 meters. And then T1 is going to be 0 seconds. And X1 is going to be 0 meters as well. In that case, the total average velocity will be pretty easy to calculate. It's going to be 0 divided by 8. We're going to get an answer that's going to be 0 meters per second. How many significant figures should it have? Well, it can only have one. All right, well, that's an easy case. How can there be going at 0 velocity, though, if I move, right? I mean, velocity involves the changing of position. How can I have gone 0 velocity between those times if I've been moving around? Okay, so that brings up a second definition I'm going to put in here, which is speed. Now, most of the time in everyday life, right, speed and velocity mean the same thing. Okay? But here, they do not. Okay? In general, as we're going to learn next week, so you don't have to know this yet, speed is a scalar, velocity is going to be a vector. Okay, you can ignore that if you don't know what that is. But speed is going to be the total distance traveled divided by time. So speed, which I'll call S here, though sometimes it's going to be called V as well, which is confusing in the book, but there you go. Distance divided by time. Okay, so between 0 and 8 seconds, what was my average speed, or what was my speed overall? Well, we have to look at the total distance traveled, which is going to be what? Let's see, 5 plus 11 plus 6. So 22 meters? Is that right? Okay. So that's 22 meters divided by the time, 8.0 seconds. And we're going to get 2.8-ish meters per second. My average speed over that time. Is that right? Someone checking me? You guys are too trusting. Okay, I don't trust you. 22 divided by 8 is 2.75, so yeah, that was right. Okay, 2.8 meters per second is the average speed, but the average velocity, in this case, was just 0, because we didn't net change any direction, or change position in the end. A whole lot of moving around, but not actually changing where we're going. We can also calculate our average velocity, say, between the first point and the third point. Let's do that. Okay, so we're going to try to calculate the average velocity between the first and the third point. We need to know, over here we define the average velocity as delta x divided by delta t. So the second point, in this case, going to be the third point, which has a position of -6, and the first point has a position of 0. Great. The second point has a time of 5 seconds, and the first point has a time of 0 seconds. Okay. How do we calculate the average velocity then? What should we do? So let's take the difference between the x's. That's x2 minus 6 minus x1, which is 0, these are both in meters, divided by T2, which is 5.0 meters, minus T1 seconds. Thank you. Good. This is why I have 100 people checking my work. I'm going to make mistakes like that all semester. And it is your job to fix me before we get further down the line and it becomes even harder to fix. So, okay.
You're going to crash the spaceship.
Well, no, because I have people checking on me. So, it's all about not assuming you're right the first time and going back and checking to make sure you've got the right answer. Okay, negative 6 minus 0 is equal to what? And this should only just have one sig fig, since these are only accurate to the meter. Meters. Divided by 5.0 seconds. What speed is that? Yeah. Negative 1. Okay. Remember, when you're dividing two numbers, the result is only as precise as the least precise input with respect to the number of significant figures. So, this only has one significant figure, this has two, therefore the result only has one. So, could it be negative 1.1 meters per second or negative 0.9 meters per second? Totally. Given our inputs, we don't know the better between those. We can't tell the difference. However, what if we want to calculate the average speed between those 2 points? Well, remember, we did go forward 5 meters and then back 6 meters, back 11 meters actually. So that's a total of what, 17? So the total distance traveled here is 17 meters. You divide that by 5 seconds. What's the average speed? Should be 3.4. Is that right? Blow it already? Okay, 17 divided by 5, 3.4. Yep, 3.4 meters per second. Why does this have two significant figures, but this only has one? Yeah. So, by adding, you can gain significant figures. So we added two numbers together, and we're able to gain significant figures. Similarly, by subtracting, you can lose significant figures. Generally, by multiplying and dividing, assuming you start with the same number, if you start with 2, you're going to end with 2, generally, with multiplying and dividing. So adding, you can increase the number of significant figures. Subtracting, you're typically going to lose significant figures. Okay. Who saw I tried to scan in the notes and put them as an announcement on website. Who saw that? Okay, who looked for it and didn't see it? Okay. When you log into WebAssign, I posted the notes from the first lecture under the announcements. I'll try to keep doing that until I find a better place to put them that's more organized where you can find them. But that's where you should look for scans of these once the lecture is over. Okay, so now we can define a third kind of velocity. That's instantaneous velocity. Okay, so the instantaneous velocity we're going to define as the velocity at a single time. So not as an average between two times. So we take one time, what is the velocity going at that one time? How do we define that? Well, we're going to say the velocity is going to be defined as, in this case, the limit as delta t approaches 0 of delta x over delta t. So imagine we took the average velocity between two different times, and we keep making that time shorter and shorter and shorter. Where are we going to get to by the end? And presumably, if you all seen this before, this is really just dx dt, the calculus derivative of the position versus time graph at that point. Oh crap. I just calculus rule my mouth there. Okay. So, we're calculating the instantaneous velocity is the calculus version of velocity. It's the amount where if you just take your position versus time graph, you want to just take the slope of that graph at any given time, the slope is going to provide the instantaneous velocity. All right, I managed to create a graph here that doesn't have a case where the positions are such that you have a different instantaneous velocity than average velocity. So I'm going to create a new plot here. What if we're actually looking more like this? Okay. Now there's a point where your instantaneous velocity is 0 here, where the slope is equal to 0. And there are times when your instantaneous velocity is greater than your average velocity, and times when your instantaneous velocity is going to be less than your average velocity. So 3 different kinds of velocities that we're going to talk about. Average velocity, where you just take delta x over delta t. Speed, where you're just going to take distance divided by delta t. And then this instantaneous velocity, where we're going to take the calculus version, dx dt, and define that as the slope at that given point in time. Who's seen dx dt before? Who has not seen dx dt before? But we'll see it very soon, I hope. Okay. So this is what you're going to learn in the first bit of calculus, is how to define this instantaneous slope on a graph as what's called the derivative. So we would call this the derivative of x with respect to t. Or the derivative of x with respect to time. Derivative of position with respect to time. Alright, how am I doing? Okay. So let's do one example of how we might be able to use the, no. Before we do the example. Okay. So if I tell you that an object is moving at constant velocity, then it turns out there's a whole lot you can know about it. Both about where it has been, where it will be, what velocity it's moving at, obviously, is going to be constant. And you can derive this equation using calculus, which I'm not going to do for you right now. But if you know that an object is moving at constant velocity, and you know its x position at any given time is going to be equal to its position at time 0 plus v times t. Okay, this is the first equation that I want you to be able to know. All right? In the case of, well, I guess I want you to know the displacement ones and the velocity ones too, but those are kind of easier. This is the first sort of somewhat complicated equation that I expect you to know. Let's put it that way. Which is that if you know that an object is moving at constant velocity, it will follow this linear equation, right? This is just, when I was in high school, this was y equals mx plus b. This is a slope equation. The slope of the line is going to be equal to vx. The y-intercept is going to be equal to x naught. So let's draw out what that looks like. Here's time, say in seconds. Here's position, say in meters. You're going to plot out where this particular object has been and is going. Because it's motion at a constant velocity, it must follow a line. So, forgive my inability to draw a line freehand, but I'm going to assume this line here. Okay, there we go. Alright, so say this is a line that corresponds to the equation x equals x naught plus vxt for a given object. X naught is the position at time equals 0. So that's this point right here. What you call the y-intercept, right? That's where this line, which could have any slope, could be anywhere, where this line crosses the y-axis, which is in this case the x-axis, but I don't want to confuse it. The position axis, that's going to be equal to x naught. And then what's Vx? Vx is going to be the slope of this line in terms of number of meters that this object traverses in a given number of seconds across the x-axis. Right? You guys have seen linear plots for a long time now. This is a particular application of a linear plot, right? So our independent axis is going to be t. If you want to know the position at any given time t, say equals 5 seconds, say, you're going to plug in, well, it's going to be equal to the time at time 0, plus it changed in some number of meters per second for every one of those 5 seconds, and so by the time we get out to 5 seconds, it's going to be in a position equal to x naught plus Vx times t. How can we use that? Let's do a problem. Yeah, I'm just going to show you my notes here so I don't have to write out this problem. Problem says a football player making a kickoff return catches a kick at the 4-yard line and has a 96-yard touchdown return. I don't understand why I stressed that out. It says that 16 seconds expire on the game clock, and that what is the player's velocity, assuming that it was constant over the course of that time. After he caught the ball, if the kick had a hang time of 3 seconds. Okay, so that's the question. First thing we need to do is define a coordinate system. So let me try to write out the question a bit again. Let's see. So we have a kickoff return. Catches at the 4-yard line. "16 seconds expire, and the hang time was 3 seconds. Okay, so that's what we're given. Remember, I said that position means nothing unless you define a coordinate system. Football fields typically have an interesting coordinate system, right? It's like centered on 50. There's like 2 origins. Mathematicians definitely did not design this. Neither did physicists. So I'm going to make a more rational football field, because the one that actually exists makes no sense to us. So normally this would be the 50-yard line. And then you have 40, 30, 20, 10, and 40, 30, 20, 10, but that's not like the coordinate system that we could possibly use. So I'm going to define a new coordinate system x that starts from our own goal line and goes to their goal line. And their goal line then is going to be at 100 yards. So this will be 0, 10, 20, 30, 40, 60, 70. Okay. So, based on this information that we've been given, we can define 2 different, we know the player's position at 2 different times, right? Okay? What's the first time? Where? 50? Sorry, I couldn't hear you. What?
I said 50.
So what's the time that we know of? 3 seconds. I think it's 3 seconds. We don't know where he is at time 0. We know at time 3 seconds he makes the catch at the 4-yard line. So let's say that time 1 is equal to 3.0. That's not 3.0, that's just 3 seconds. I want to add a 6 here. One doesn't deserve to be there. 3 seconds. And at that point, position 1 is going to be equal to, what was it, the 4-yard line? 4 yards. Okay. Great. The second time we know is going to be x2 and t2. What time does that correspond to? 16 seconds. And what position? 100. Yep. In our more rational coordinate system, their goal line is at 100. Yes? No, the 16 seconds is the time on the game clock. So that's total time relative to 0 point, which is when the game started. This is to make it harder. So, yes. So what's the total change in time between when the ball is caught and when you go across the goal line? 13 seconds. Okay, so this is to make a delta t that's a little less trivial. So, in this case, the average velocity is going to be equal to delta x over delta t. It's going to be x2 minus x1 over t2 minus t1. It's going to be 100 yards minus 4 yards over 16 seconds minus 3 seconds. Okay. What's 100 yards minus 4 yards? How many sig figs? 2. Yep, it is actually 96. Right? Because this is, as each of these are accurate to within 1 yard, this actually should be 100 dot. Because we know that's exactly 100 yards, right, in our coordinate system. So 100 minus 4 is going to be 96. 16 minus 3 is going to be 13. How many sig figs should that have? Also 2, because this should be accurate to the second. What's 96 divided by 13? Ugh, okay. So it's taxing my ability to do it in my head. 7 or 8, something around there? 7.4 in total. Okay, thank you. 7.4, and that's yards per second. Okay, not a NASA approved unit, but it is a correct unit in this particular case. So you must have been moving at 7.4 yards per second to be able to, yeah, that's fairly fast. Well, how fast is that really? Let's convert that to a unit that makes more sense. So 7.4 yards per second. You convert that to meters per second first. Or we can convert it to miles per hour. What should we do? Who wants? Miles per hour? Okay, let's do that. All right. So let's see. 1 hour is equal to 3,600 seconds, right? 60 times 60. So these are going to cancel. How many yards in a mile? Forget it. Okay. Let's convert it to feet
1760.
first. There's 3 feet in a yard. Those cancel. And there's 5,280 feet in a mile. Okay. Yeah. You're getting 17?
1760.
1,760? Oh, as far as yards per mile? Yeah, that sounds right. Okay. So let's take 7.4 times 3,600 times 3 divided by 5,280. And we get, on my calculator, 15.136. But how many sig figs should I have? 1. 2 actually, because it started with 2. This 3 feet per yard, this has an infinite number of sig figs, right? Because that's just defined. This should be 15 miles per hour. So that's pretty fast. That's like a 4-minute mile, right? But for a sprint over 13 seconds, that's not crazy. It's super fast, but it's not, I don't think it's unreasonably fast. Or not. Okay. Let me do this problem a way harder way that hopefully will be illustrative of the way you can use this without using a lot of thought in the future to be able to figure out what's going on. And I want to harken back to our equation, x equals x naught plus bx times t. So the question was how fast was he going? So the answer was 7.4 yards per second, so we could figure that out. What if you wanted to be able to know where he was going to be at any time t? Assuming he was just going to keep running straight through the wall and had been running that way for all eternity. In that case, we could just try to calculate what these numbers are, x naught and vx, just straight away by using the values we have. So we know that x position 4 is equal to whatever x naught is plus whatever vx is times time, 3 seconds. And simultaneously, we know that at time 16 seconds, he must be at 100 yards. Okay. So now we have two equations and two unknowns, which brings you that warm, fuzzy feeling, knowing that you can solve this using simultaneous equations. Who does that make feel warm and fuzzy? Who? Me. That's great. That's so fun. Let's do that. How should we solve these two equations? Who has a favorite way to solve simultaneous equations? Substitution. All right, what should we substitute for? X naught. All right. So let's solve this first equation for x naught. It's going to become x naught is equal to 4 yards minus vx times 3 seconds. Let's plug that in then to the second equation. Now the second equation is going to say 100 yards is equal to 4 yards minus vx times 3 seconds plus vx times 16 seconds. Great. We can subtract 4 yards from each side. This becomes 96 yards equal to vx times 13 seconds. And we get an equation for vx that is very familiar to us. 96 yards divided by 13 seconds, which we just heard was 7.4 yards per second. So that's what vx is. How do we go back and figure out what x naught is? We go back in here. That's equal to 4 minus vx times 3 seconds. So that's going to be 22.8 negative 18.8. That can't be right. It has too many sig figs. This should only be as precise as the least precise input. So that is actually going to be negative 19 yards with the x naught. So now, if you were to know this, now that you know x naught and you know vx, right, you can go and plug those in, and for any arbitrary time, like where was he at time 5 seconds, or time 8 seconds, or 8.7 seconds, you can calculate exactly where that position would have been on the field as it's moving forward. Okay, as you might imagine, this is the simple version. And in the future, I just can't help but make it more complicated, because that's who I am, okay? So, today we talked about simple motion in one dimension where velocity was constant, okay? So we define a couple different terms. We define position, which must be relative to a coordinate system or to another object, right? There's no absolutes in position. We define displacement, which is the change in position, delta x, so x2 minus x1. We talked about velocity, 3 different kinds of velocities, because that's the way we roll. We talked about average velocity, which is just displacement divided by change in time, so delta x divided by delta t. We talked about speed, which is the distance traveled divided by the time. And we talked about instantaneous velocity, which is the calculus version, where you get the slope of the position versus time graph at a particular instant in time. Yes, question? Yes, so I would write instantaneous velocity as just vx. Average velocity I'll write as v average, and speed I will define as s or something separate and distinguishable. And then we had your first complicated equation, which is not all that complicated. Wait till I get to the complicated one. This is nothing. Okay. Which is that if you want to know an object that's moving at constant velocity position in any arbitrary time, you can get that from x is equal to x naught plus vx times t. Okay. For next time, we're going to let velocity not be constant. And for that, you should read sections 2.4, 2.5, 2.6, and 2.7. We will talk about that more complicated situation on Wednesday. See you then.